Hello, this is Peter Minnett, and I'm very pleased to have this opportunity to present over 2 decades of skin sea surface temperatures derived from the moderate resolution imaging spectroradiometers on the NASA Terra and Aqua satellites. I apologize if aircraft noise in the background becomes distracting, but where I live that is fairly standard, unfortunately. But first, let's go back in time. In the 1990s, Neville Smith and Michel Lefebvre were developing the idea of a global ocean data assimilation experiment that became known as GODAY to conduct a 10-year international demonstration of the feasibility and utility of real-time global ocean forecasting. Of course, sea surface temperature derived from satellites was seen as an important component of GODAY, and at that time there were many groups worldwide deriving sea surface temperature from different instruments on different satellites using different algorithms, and it wasn't clear whether these sea surface temperature fields were at all compatible. And that led to the establishing of the GRIST pilot project under the leadership of Craig Donlan to try to bring some order to the production of sea surface temperatures for use in GODAY. Going back a little bit further in time, NASA was developing the concept of the Earth Observing System, which was to take measurements of all the components of the Earth's climate system, primarily from satellites. Amongst a group of satellites were 3 that were to be launched in sun-synchronous polar orbit to carry extensive suites of state-of-the-art instruments, and these became known as Terra, Aqua, and Aura. Terra and Aqua focused on the atmosphere and surface variables, and Aura focused on the atmosphere. Because of the very high data rates of these sensors, there were significant developments in the ground segment to accommodate the processing and distribution of these measurements. So NASA Earth Observing System and GRIST have a common history. Terra was launched at the end of 1999, and Aqua was launched in early 2002. For those of you who remember the year 2000, there was a great deal of concern about the possibility of the Y2K bug interfering with many computerized activities. And NASA was not unique in thinking it was a bad idea to have computers on spacecraft running at midnight on December the 31st, 1999. So even though the satellite was launched successfully, it wasn't powered up until into January of 2000. The planned lifetimes at that time seemed very ambitious, but since we're now over 20 years beyond the launch of both satellites, it is a remarkable testament to the engineers and physicists and computer scientists who worked on this program. Both satellites carried a version of MODIS which were intended to be essentially identical. There were plenty of other instruments on each satellite too. MODIS is a large instrument, and it is shown here on Terra and Aqua. The cutaway diagram shows the large rotating scan mirror, and down towards the bottom of the slide is an opening for the Earth view. The infrared calibration was done by a grooved black body target and a view of cold space. There were many innovations incorporated into the design of MODIS, and early on in the Terra mission it became clear that innovations was another word for challenges. There are 36 spectral bands covering a very wide spectral interval in MODIS from the blue into the infrared, and these had differing spatial resolutions at nadir, with 2 visible bands having 250 meter resolution, others having 500 meter resolutions, but the majority at nadir had a 1 kilometer resolution. And there were multiple detectors per spectral band, 40 detectors in the high resolution band going through to 10 detectors at the 1 kilometer resolution bands. These were mounted on 4 separate focal plane arrays, and the radiation from the Earth view and the calibration targets was directed onto this cluster of detectors using a 2-sided paddle wheel scan mirror. The infrared black body was a grooved plate, and the calibration included measurements of this, as there were many thermometers embedded in the plate, and a view of cold space. The spectral bands are shown here, and I know this is an eye chart, but these are the visible spectral bands and these are the infrared. And they included what was at that time a fairly standard split window pair at 11 and 12 microns, but they also included a pair of very narrow bands in the mid-infrared atmospheric transmission window, which was new to MODIS. The upper panel shows the calculated atmospheric transmission for 3 atmospheres that span the range encountered over the world's oceans. The relative spectral response functions for the bands used to derive skin SST from the Aqua MODIS are shown in the lower panel. Those labeled 31 and 32 are at 11 and 12 microns, and these are about half a micron wide, which is about half the width of the comparable channels in practically every other satellite-borne infrared imaging radiometer. In green and blue, we see the relative spectral response functions for the very narrow bands in the mid-infrared transmission window. Looking at the spectra above, we see that the variations at these wavelengths, going from the poles to the tropics, is much smaller than at the bands 31 and 32. Thus, the variability in the signal caused by atmospheric variations is much smaller at 22 and 23. However, we note that the emission, shown here as the Planckian emission at temperatures 0 through to 30 degrees C, is much smaller than at 11 and 12 microns. However, the relative changes in the signals at 22 and 23 are much greater than at 31 and 32, so there is a radiometric advantage at taking the mid-IR measurements. However, due to scattering of solar radiation during the day, measurements at 4 microns can only be used at night to derive skin SST. So, here are 4 diagrams of the 4 focal plane arrays labeled visible, near infrared on the left, shortwave and midwave IR, and longwave IR on the right. They're not arranged as shown in the diagram, but are positioned independently within the instrument. So the alignment is very important. The small plus sign in the center of each shows the optical axis of the instrument. The multiple bands present a couple of problems. One is that there is the risk of banding in the imagery if the calibration of each of the detectors is less than perfect. The other potential issue, which turned out for some bands to be quite a problem, is the risk of optical crosstalk. And this brings us to the MODIS scan mirror. The photograph on the right, which looks like a genie emerging from a bottle, is in fact a picture of a technician in the clean room holding the scan mirror assembly. He's holding the motor. And remember that there are two sides to this scan mirror. The mirror is made of beryllium, nickel-plated, coated in silver, and finished with a protective layer. This protective layer was included to improve performance in the visible wavelengths. However, it introduced a rather difficult artifact in the infrared, in that the reflectivity of the mirror surface is not only wavelength dependent, but also dependent on the angle of incidence on the mirror surface. The diagram at the middle at the bottom shows the angles of incidence on the mirror for various stages in the rotation of a mirror. N is normal to the mirror surface, and we see that just to the right of normal is the start of the Earth view, which continues through nadir to the Earth scan stop. On the other side of normal are the calibration sources in the visible and the onboard blackbody and the space view for the calibration in the infrared. This means the angles of incidence on the scan mirror for the Earth view do not include those used in the calibration. And that was a bit of a problem. The diagram on the left shows the angles in the form of just one rotation of the scan mirror. So nadir is straight down and labeled 0. Earth scan starts at -55 degrees and ends at +55 degrees. And the black body and the space view port are at different angles. So all of these problems were overcome. The image here, taken from very early in the Terra mission, May year 2000, is showing the Gulf Stream off the east coast of Florida and the cooler water coming down from the Labrador Sea. To the north, the darker grey is the presence of clouds. This shows that the banding caused by multiple detectors has been solved. It shows that the response versus scan angle has been resolved, and that the sea surface temperatures look very clean. So now we have confidence in the integrity and validity of the infrared measurements. We have to decide how to remove cloudy contaminated pixels from the SST retrieval process. At the start of the two missions, we adapted the decision tree approach, which was developed for the AVHRR Pathfinder SST program. And in these, a number of tests are applied to pixels or groups of pixels relating to the measurement, the variability in space of the measurements, the differences in channel measurements, and so on, at different wavelengths. incorporating in the daytime visible reflectivity. And for a pixel to be declared cloud-free, it had to pass all of the tests. It soon became apparent that this was far too stringent a set of tests, and so we turned to an alternative approach based on machine learning, which was given large numbers, hundreds of thousands of matchups between the brightness temperature measurements and in situ measurements, more of this later, to determine an alternative approach, which became known as the alternating decision trees. The thresholds and the tests themselves were determined by machine learning, and it became apparent that this was a much better approach in that it classified far more pixels as being cloud-free or free from cloud contamination. Here we see at high latitudes in the Southern Ocean. On the right-hand side, we have a daytime data, an L3 field from MODIS, with the alternating decision tree cloud mass compared to, on the left, the binary cloud mass. The Mediterranean also was better sampled using the AD trees, the alternating decision trees. So that was good progress. And that has been applied to the current version of the MODIS-skin SST data. So having derived confidently cloud-free pixels in the bands in the infrared wavelengths needed to derive sea surface temperatures, we require a correction for the effects of the intervening atmosphere. The standard split window correction, which is used for both day and night measurements, is taken from the nonlinear SST, NLSST algorithm of Charlie Walton et al., with 3 additional terms needed to correct for residual effects, artifacts of the MODIS instrument. The 2 mirror sides of the flat scan mirror are not identical in their reflectivity, and neither is the correction for the RVS in the infrared perfect. So there are 3 additional terms to correct for these small residual artifacts. The T surface is a background SST which is used to scale the brightness temperature difference correction. And this is because the brightness temperature differences in band 31 and 32 can be the same, but for very different types of atmospheres. Therefore, if a single correction in brightness temperature difference is applied, there can be significant regional bias errors. This can be largely corrected for by scaling the brightness temperature difference correction by an estimate of the surface temperature. It turns out the surface temperature estimate here does not have to be terribly accurate, as the sensitivity of the derived sea surface temperature to errors in this T surface term is quite small. To begin with, we used the background SST value taken from the NOAA Reynolds OI optimal interpolation SST fields, but after a period, the performance of the AVHRRs used to derive this OI field began to degrade, and we found that using the Canadian Meteorological Centre Global Foundation temperature was a much better estimate for the T-surface for this algorithm. The 2 narrow bands in the mid-infrared transmission window because they show much less variability to atmospheric variations, the atmospheric correction algorithm is somewhat simpler, but it does retain 3 terms for the MODIS-specific artifact correction. Now, the coefficients for each of the algorithms is derived from an analysis of the brightness temperatures and in situ measurements, mostly taken from the NOAA IQUAM data. The coefficients are divided by month of the year and divided into 7 latitude bands. That is for matchup south of 40 degrees south, between 20 and 40 degrees south, between the equator and 20 degrees south, between the equator and 20 degrees north, and so on, with the most northerly band being north of 60 degrees. So there are 84 sets of algorithms, of coefficients for each algorithm. And what does it look like? Well, here we have a comparison in the 7 latitude bands between Terra MODIS SSTskin versus the subsurface temperatures from the IQUAM drifters. And these are box plots for the entire mission of the Terra MODIS up to about 2022. The red line is the average difference between a skin temperature and a subsurface temperature at the depth of the buoy measurements of minus 0.17 Kelvin. The panel on the left is for the split window SST, and the panel on the right is for the 4 micron SST, referred to as SST4. We can see that there is remarkable consistency over the 20 years of these data sets. The Aqua MODIS plot is essentially identical to this. There are gaps caused by instrument shutdown or computer issues in the processing. If the IQUAM drifters are giving a good representation of the subsurface temperatures, then from this we can argue that the MODIS SSTs are giving a good representation of the skin temperatures of the ocean. And as intended, the SST4 shows less variability than the split window. Now, there is a difference, of course, between the skin of the ocean, its temperature, and the subsurface temperature derived from a thermometer, even at a depth of centimeters. And this is called the skin effect. In the derivation of the coefficients for the algorithms, the atmospheric correction algorithms, and in the derivation of estimates of the accuracy of the retrievals, we take a global average value of minus 0.17 Kelvin. This value is actually remarkably robust, but there is a change due to variations in heat flux and primarily wind speed, which thus far we have not been able to replicate in the algorithms. The diagram on the right shows the fitted SSTskin effect as a function of wind speed for a set of 4 measurements. The one labeled data in black is actually sail drone measurements. The intercept at high wind speed is there for these fitted curves are all within 20 millikelvin, and that would be very unusual if there were systematic errors in how these shipboard measurements and sail drone measurements were derived. So this variability is not properly resolved in the estimates of accuracy derived from comparisons with subsurface drifter measurements. And the better approach is to use an estimate of the skin SST taken from ship radiometers, and we use one called the M-AERI and have been using various versions of this type of instrument since 1996. It's a Fourier-Transform Interferometer with black bodies, 2 black body cavities used in at-sea calibration before and after each measurement cycle. A measurement cycle is a measurement of the sea surface emission, the atmospheric emission at the angle that is reflected into the at the sea surface into the measurement of the sea emission, and at zenith. So they're calibrated every few minutes. And before and after deployment, the calibration is tested against SI traceable laboratory black bodies, which are periodically confirmed by tests with NIST and NPL. And the M-AERIs run autonomously. Up until COVID, we had 3 on cruise ships and 1 on a research vessel. And for the few years up to COVID, it was the NOAA ship Ronald H. Brown. And the SST is derived from spectral radiance measurements at a wavelength of 7.7 microns. I can discuss this offline if you're interested. So following COVID, the Ron Brown resumed research cruises with a much reduced scientific crew starting in October 2020, and the tracks colored by the M-AERI retrievals of skin SST are shown here. And then for 21, 22, and 23. And then the ship went into dry dock for a major refurbishment, and it's expected to return to service later this year. We also had instruments on Royal Caribbean cruise ships, which were idle during the COVID pandemic, and we resumed taking measurements in late last year on the Celebrity Equinox. And this is a picture from the dock of the Celebrity Equinox, and there is the M-AERI, a better view of the M-AERI. And here it is after being refurbished and is deployed now. It's currently in the Mediterranean. But before it went there, it was doing circuits around the Caribbean, the left-hand side from October to the end of 2023, and the right-hand panel 2024 up until April. So these are the estimates of the accuracy of the MODIS skin SST retrievals, Terra MODIS above, Aqua MODIS below, by comparisons with the M-AERI. And the left-hand panels are for the split window SST and the right-hand panels for SST4. So we see that the means and the medians for quality level 0, which is the best quality level, are pretty good. And the robust standard deviations for SST4 are also very good. Both spacecraft have now consumed all of their onboard propellant needed to maintain the orbit. And so for the last several years, the orbits have been drifting. Terra has been drifting earlier in the day and Aqua later in the afternoon, as shown here. The satellites will be passivated, I think is the correct term, when the angle of the solar radiation on the solar panels is insufficient to provide enough power for the instruments to function. So to summarize, throughout the period of GRIST, near continuous retrievals of SSTskin have been made from MODIS on Terra, and since 2002, MODIS on Aqua. There have been several sets of algorithm improvements, with the last complete reprocessing in 2019. The SSTskin fields are consistent and have sufficient demonstrated accuracy for many scientific applications. For nearly all of their missions, the satellites have been in maintained orbits but are now drifting. The MODIS SSTskin fields L2P, L3, and as part of MUIR are some of the most frequently downloaded files from the JPL PODAC. Many people have contributed to this project over 2 decades, and we have enjoyed funding from NASA and support from NASA Goddard and the PODAC and Royal Caribbean, and especially the Ronald H. Brown Ship of NOAA. Thank you.